we consider another method how to create an interpolating polynomial, and the problem statement is written here. We have a table of points. We have table of points x, and f of x, x0, x1, and so on, x0, f1, and so on. And we are going to find a polynomial of lowest possible degree that passes through these points. And here on this slide, you may see the general form of this polynomial. Pn equals to a0 plus a1 x minus x0 plus a2 x minus x0 x minus x1 and so on. Suppose that I have 2 points, only 2 points, x0 and x1, only 2 points. Using only 2 points, I can write a polynomial of first degree. This is the polynomial of first degree that I can write using 2 points. If I have 3 points, I can write a polynomial of second degree. These 3 terms correspond to the polynomial of the second degree. And the main question is how to find the coefficients a0, a1, a2, and so on. If somebody told me these coefficients, I can say that, okay, excellent, I can write a polynomial. Well, and on previous lesson, I show you how to compute these coefficients. The coefficient a0 just equals to the values of the function. A0 equals to f of x 0. And after that, how to find a1? A1 equals to f1 minus x0 over x1 minus x0. Well, actually to find all of their values a0, a1, and so on, I should build so-called divided difference table. On this table, or let me open this table on the full screen. On this table, the first column, or I can write it as the first row. The first row is just the values of the function. This is just the values of the function. The next column, first divided difference. I should take 2 values of the function over 2 x's, f1 minus x0 over x1 minus x0. This is for this one. The next, f2 minus f1 over x2 minus x1, and so on. This is the first divided difference. The first divided difference, xi plus 1. As far as each of these formulas includes 2 points, so if I have here n plus 1 points, that are numbered from 0 to n. The first how many it will be the first divided differences if I have n plus 1 points. Suppose I have 3 points. 3 points. 0, 1, and 2. How many first divided difference? It will be 2, right? 1 minus 0 and 2 minus 1. And after that, using these divided differences, this one and this one, I can compute the next divided difference. This minus this minus this, like written here. This minus this. I don't want to rewrite all on the board. Let me denote this formula as 2 stars, this formula as 1 star. How to compute? 2 star minus 1 star over the difference between x's, the largest distance, x2 minus x0. It's exactly the same is written here. Exactly the same is written here, x2 minus x0. Here x3 minus x1, x4 minus x2, and so on. Next divided difference, I should take 2 previous divided differences over the difference between them over x3 minus x0, x4 minus x1, and so on. So these divided differences will form a table like triangle. Here we have n plus 1 values, on the lower part of triangle, and on the upper corner we have only one divided difference. And after that, how to write this polynomial? I can take only, I should take this upper divided difference, f of x0, f of x0, x1, f of x0, x1, x2, f of x0, x1, x2, x3, and so on. And substitute it into this formula. Substitute it into this sum, and after that I will write a polynomial. For example, polynomial of degree 1. It will be f of x0 plus f of x0, x1 times x minus x0. This is a polynomial of degree 1. How to write a polynomial of degree 2? Polynomial of degree 2, it will be a polynomial of degree 1, previous polynomial, plus f of x0, x1, x2 times x minus x0, x minus x1. I add one more term to the previous polynomial, to the previously defined polynomial. And so on. And using, we did it online on previous lesson, I asked you to compute a table of divided difference using this initial data. And if you have computed this table of divided differences, you can write a Newton interpolatory polynomial. And on this lesson, I want to show you how it can be done in a program. Because our subject is called computing mathematics, it means we should compute something. I can show you how we can use this formula to compute an approximation of a function in Visual Studio. Well, let's consider this program line by line. I turn off the sound at one. Well, first, max size is just the maximum size of this table. Actually, it will be less than 10, but I declare it just to declare the array. So this is the maximum size of the array. This is n corresponds to the degree of a polynomial. So if I assign n equals to 3, it means I have 4 points. 0, 1, 2, 3, 4 points. And actually I have 4 points here. x0, x1, x2, and x3, and 4 values, 1, 3, 2, and 6. These values correspond to this table. Well, the array X is a one-dimensional array. It's an array just for the arguments. But F I declare as two-dimensional array. F is an array to store this divided difference table. I will store it row by row, like on a board. The first row of this table will be just the values of the function f0, f1, f2, f3, and so on. The second row, it will be the first divided differences, this, next, and so on. Next row will be second divided difference, this, and so on. So I should declare a two-dimensional array to store the table of divided differences. And the first row of this table will have the same values as the values of the function 1, 3, 2, and 4. Well, this loop, let me delete this unnecessary space. This loop is to compute the divided differences. I should write here two loops, nested loops. First loop, from I equals to 1, I smaller than n plus 1, or I can write it I smaller or equals n, and here also smaller or equals How to compute the divided difference? I should take the value from the previous row and j plus 1 minus f of j. Well, like this. So how to compute this? I take previous row and next column, the index I corresponds to the rows, index j corresponds to the columns. J plus 1 minus j. So 1 minus 0, 2 minus 1, and so on. Over x, j plus 1 minus xj. For I equals to 1. How to compute the next divided difference? This one. I should take the previously defined divided differences f I minus 1. It means from the previous row, next column, j plus 1 minus f of j. But here, over x j plus I minus xj. Because the difference of x's, difference of x's, the distance between x's will increase from row to row. Here, 1 minus 0. Here, 2 minus 0. Next row, it should be 3 minus 0. And so on. That's why I should write here j plus I minus xj. And that's all. This loop computes the table of divided differences. This loop is just to output this table. This loop is just to output this table. Let's look to this table. I comment the last part of the program now. We discuss about it later. And here n equals to 3. Let's run the program. And we see the table of divided differences. This is the values of f, 1, 3, 2, 4, or 1, 3, 2, 6. The next line, first divided difference, 1 minus 1, 2. Next line, we have only 2 values, minus 3, 2 over 3, and 1. Next line, only 1 value, only 1 divided difference. Maybe to let me to just 2 values after there. See out precision. I output only 2 numbers after two digits after the point. If I comment this line, compiler will output by default 6 values on default. But if I want to output more or less values, I should use cout precision. I want to output 2, just 2 values. I want to output 10 values, cout precision 10, and we see 10 values, 10 digits after the point.
And what's the difference between precision and cout and putting the arrows?
the difference between what?
Placing the dot.
What? Please write on a board or type. When you put these arrows, it means that you output something to output stream, output something to the screen. Here you output the end of line symbol. Here you output space. Here you output the value. But when you type dot, it means you change some options of this output stream. You don't output nothing at this time, but you change some properties of this output stream. So it's not when you type this sign, it means you output something. When you press point, it means you change some properties. In this case, I change the number of digits after the point. Okay, this is a table. This is a table of divided differences. And to output the polynomial, I should take what divided differences? Only the first, with the point 0, 0, 0, 1, 0, 1, 2. This divided difference will correspond to the first column of this table. 1, 1, minus 0.67 and 0.33. Well, and maybe, I don't know, because I don't output this value to the screen. But if I have these values, suppose that I have it. I know this number, this number, this number. I know these numbers. After that, the main point, the main question, it is how to compute the value of the polynomial. Let's run this program again. And wait a minute. Computer thinking. Well, the zero divided difference is 1. You know how to write P1. P1 of x to the 1 plus, let's take the next, 1 times x minus x0. What is x0? I don't output it here on the screen on this program. What is 0? The first 0 is 0. The first 0, x minus 0. So P1 will be just 1 plus x. 1 plus x. How to compute P2? P2, you should take P1, 1 plus x, plus, let's take the next divided differences. divided difference. It's also 1. Sorry, not 1, but minus 0.67. But minus 0.67 is minus 2/3. You should minus 2/3 times x minus x0, x minus x1. x1 is 2. And this is the polynomial of degree 2. And so on. To compute a polynomial of degree 3, you should take polynomial of degree 2 and add one more term. But after that, when we find these polynomials, it's very the next question. How to compute the value of this polynomial? Because here it's just a formula. It's just a formula that is written on a board. But I want to compute the value of this polynomial. I want to substitute here some x. For example, x equals to 1. Because x equals to 1 is skipped here. I have only 0, 2, 3, 5. No x equals to 1. But I want to compute it. I want to compute, for example, p1 of 1 or p2 of 1 and so on. How to compute p1 of 1? What will be the value of p1 of 1? What? 2. 2. It's 1 plus 1. It's 2. P2 of 1. 2 minus. What is P2 of 1? It will be 2. Here x equals to 1. This is 1. This is minus 1. Minus on minus gives us plus. And we have 2 plus 2/3. That equals to, it will be 2.6666. It will be 8/3. But we compute these values in mind. But how to compute it in the program? How to compute it in the program? And this loop computes the value of the function. Let's check. Let's assign the degree of the polynomial 1. N equals to 1. And let's compute this value at the point 1. We know that it should be 2. Yes, P of 1 equals 2. How it can be computed? 2 loops. The first loop. As you see, this is a sum of products. This plus this plus this plus next for the next polynomial, and at each element of this sum, I should compute the product of the x's. X minus x0, x minus x1, x minus x2, and multiply it on the divided difference. And here I implemented using two loops. First loop, I changes from 1 to n, let it for simplicity like this, and the inner loop computes the product, the value of x. Here I denote x1 as a point at which I want to compute the value of the polynomial. X minus x j minus 1. I compute the product in P, multiply it at the divided difference, and plus to the value of the polynomial. So these two loops, using these two loops, I can compute the value of the polynomial. Let's check it. Again, for n equals 2. N equals 2, the value of 1, 2.7. But I put precision equals 2, let me remove it. 2.66666, because if I put precision equals 2, just 2.7. Well, again, I told you that there is a very simple way to check is your polynomial correct or not. Because if it's correct, the value at the point x1 must equals to the value of f1. And I can check it in the program. What is the value of x1? 2. The value of f1, it must be 3. Let's assign 2. The value of p of 2 equals to 3. So our computation is correct. I can change the degree of polynomial 3. But value at this point will be the same. So here I just I want to show that the formulas that we write on the board, on the paper, these formulas can be transferred to program. We can write a program that can use these formulas to compute the value of the polynomial. And again, what is the main point of interpolation? I want to repeat it. I have only a few values, x0, x1, x2, for example. And I know only these 3 points. But after I build an interpolating polynomial, I can compute the value of the function at any point that I want. I can take any point, and at this point I can compute the value of interpolated polynomial and say that this value will be approximation of the function. So after that, I can compute the approximation of interpolating polynomial at any point. Here I can take 2, but I can take 2.2 and compute the function value at the point 2.2. It will be some other value, or even 20.2. Of course, I get some large value, but I can do it. Or 2.7. Any point. I can take any point and compute the value of the polynomial. And this value will be approximation to the value of unknown function. Well, that's all that I want to say about interpolation. Let's finish the first part of our lesson. And the next part, the next lesson that will start 10:50 will be devoted to numerical differentiation. The next part of our lesson, numerical differentiation. Now I stop sharing. Let's have 10 minutes break, and after the break we continue this lesson. Well, we start in a few minutes the next part of our lesson. Maybe I share the screen. Okay. Let's start the second part of our lesson, and this second part will be devoted to the problem of numerical differentiation. So, as usual, we first consider the general problem statement. After that, we discuss about some general approach called Taylor's series approach for deriving of numerical differentiation formulas. And after that, we consider some particular cases, some formulas for numerical differentiation. And the problem statement for numerical differentiation is presented here on this slide. And in general, the information for this problem is the same as for the problem of interpolation. We have only a few points, x0, x1, x2, and so on. And we know the values of the function only at these points, f0, f1, f2, and so on. And the question is, can we use this information to find the derivative f prime c, f prime at some point c. Let me explain this problem statement. When we consider some mathematical preliminaries, I ask you about what is a derivative, and I ask you about the rules of differentiation, and you told me some simple rules. For example, if f of x equals to x power n, what can you say about f prime x, the first derivative of
n x to the power n minus 1.
yes, n times x n minus 1. This is the first one. For example, if f of x equals to sine x, then the derivative is cosine. If f of x is e power x, the derivative is the same. Well, so when we know the function, when we know that f of x equals to sinus x, we can find the derivative. The derivative of cosine, and we can compute the derivative at any point. If f of x is x power n, we can compute the derivative, and after that we can compute the derivative at any point. But if we don't know the function, we know only these few values, how we can compute the derivative? This is the question. We don't know the function. We know only the values at some points. Well, and if we know only this table, and if we don't make any other suppositions about the function, the problem is unsolvable. And we should make some supposition about f of x. For example, if f of x is just, we know that f of x is just a continuous function, this information is useless. So we cannot find the derivative. But if we know that f of x is a polynomial of degree n, then this table of n plus 1 points completely define this polynomial. It can be written as interpolating polynomial in Lagrange or Newton form, but these n plus 1 points in any case completely defines the polynomial. And in this case we can recover p of x precisely, and we can compute p prime at any point c. And after that, we can use p prime c as an estimation of f prime c. This, the last sentence maybe is the main from this slide. We have a table of these values. Using this table, we can find a polynomial p of x of degree n. We can recover it, we can find it precisely. And after that, we can find a derivative of this polynomial, p prime of x. And we can say that this derivative will be more or less the same as f prime of x. F of x is unknown. But we know that Pn of x is approximation of f of x. That's why we can say that P prime of x will be approximation of f prime of x. Again, I show you this picture. This picture illustrates that there are a lot of functions that pass through given points. Here we have 6 points, x0, x1, x2, x3, x5. And there are infinitely many number of functions that pass through these points. But only one of these functions will be the interpolating polynomial of degree 5. Because 5 points defined, 6 points defines the polynomial of degree 5. Only one of these functions will be their polynomial. Well, I repeat the idea. It's a general idea. Maybe we consider it on the next lesson, but I repeat it now again. So we have a table of the functions, function values. We can find a polynomial, but we don't know the function. But we can say that the polynomial approximates the function. And as far as the polynomial approximates the function, we can say that the derivative of the polynomial will approximate the derivative of a function. But maybe the first way for deriving numerical differentiation formulas, the first way we consider not related with interpolation, but exactly from the definition of numerical differentiation. Again, we consider on the first lesson what is a derivative. What is a derivative by definition? If we have a function f of x, then the value of the derivative at the point x, by definition, is the limit when h tends to 0, f of x plus h minus f of x over h. In theory, to find the derivative, we should compute the limit when h is smaller, very close to 0. But actually, this formula gives us a very simple way to find the approximation to the derivative. Let's consider some fixed value of h, small but fixed. And let's find the value according to the formula 1, f of x plus h minus f of x over h. When h is some fixed small number. For example, h may be 10 power minus 3, 10 power minus 4. It's a small, but it's not tends to 0, but a fixed small number. And for linear function, this formula is exact. It means that it yields the correct value of f prime x for any non-zero value of h. You can take any value of h and you can get the correct value for f prime x. Let's discuss about this case in details. Suppose that we have a linear function f of x equals to ax plus b. Suppose that we know that the function is linear, ax plus b. What is the derivative of this function? What is the real derivative of this function, f prime of x? F prime x, what is the real derivative?
1.
No. Why 1?
This is a constant.
But what constant? Exactly, in this case, f of x equals to ax plus b, f prime x. Ax?
A. No, it's A.
Just a.
Just A.
Just a. This is, according to this rule of differentiation, f prime x equals to a. According to the rules of differentiation, f prime x equals to a. Now, suppose we forget this rule and let's apply formula number 1 to find their derivative. What is let's apply formula number 1. F of x plus h minus f of x over h, where h is some positive value, some fixed number. What is f of x plus h? You should substitute x plus h here. A x plus h plus b. It's f of x plus h minus f of x. What is f of x? It's just ax plus b. Over h. And if I open all the brackets, minus b cancels with b, ax cancel with minus ax, and I have only one term, ah, and over h. H also cancel, and I have a. For any value of h, because h is cancelled. It means that the formula 1 gives us exact value for linear function. The value will be exact. If the function is not linear, in this case, this value will be not exact, but some approximation of a real value. You see that in the formula number 1, it's written as approximately equals to f of x plus h minus f of x over h. And when h is greater than 0, when h is positive, this formula is called forward difference formula. And when h is negative, is called backward difference formula. Yeah, this formula is correct for all values of h, both positive and negative. But when h is positive, it's called forward difference formula. When h is negative, backward difference formula. This picture illustrates the situation. We already discussed about it, that what is the geometric interpretation of the derivative. Do you remember? Geometric interpretation of derivative at some point is the slope of a tangent line at this point. It's a slope of the tangent line. And this picture illustrates the situation. Suppose that x0 is a point where we compute the derivative. And f prime of x0 is the real value of the derivative, and it corresponds to the slope of the tangent line. This is a tangent line, and its slope equals to f prime of x0. But if I consider this formula, formula number 1, for some point x0 and x0 plus h, it will correspond to the slope of this second line that passes through 2 points. The point f of x0 and the point f of x0 plus h. This line. And you see on this picture that the slope of this line is more or less the same as the slope of the tangent line.
Yeah.
Moreover, if I take this point closer, and closer, that corresponds to small h. If h will be smaller, and smaller, this second line will be closer and closer to the real tangent line. So the slope of approximated line will be closer and closer and closer to the real derivative. Is it clear? The situation? Okay, to understand how it works, to understand it, I ask you to solve a very simple problem. I ask you to all of the students, including the students who connect to us in Microsoft Teams. Let's take the very simple function x power 3. Let's consider the point 1. Let's take x0 equals to 1. And I ask you to find the real value of the derivative at this point. And I ask you to find the approximated value of the derivative using h equals to 0.1. Suppose that h equals to 0.1. The function is x power 3. Please find the real value of the derivative at this point and the approximation. Using the formula that is written here. Some computations you can make with your calculators or on computer. Well, what is the real value of the derivative at the point 1, at the point x0 equals to 1? The real value according to the rules of differentiation. What is the real value of the derivative? 1? No. The real value according to the rules of differentiation. So this problem includes two formulas. The first formula that gives us the exact value. The exact value according to the rules of differentiation. We already read just 5 minutes before. What is the derivative of x power 3? By 2x squared. 3x squared. But we consider the point x0 equals to 1. What is the value of the derivative at the point x0? 3, not 2. 3. This is the real value of the derivative. The real value is f prime of x0 equals to 3. Now, suppose we don't know this real value, but we know only the function and the step. Step is 0.1. How to compute the approximation to this real value? We should use this formula, f of x0 plus h. It's written here also, f of x0 plus h minus f of x0 over h, when h is 0.1. And f of x is x power 3. What is the approximation value? What we should do to compute it? First, we should compute these two values of the function. F of x0. What is f of x0? This formula includes two values of the function. F of x0. What is f of x0? No idea.
It's 0. It's 1.
0 or 1?
1.
1.
Yes.
Yes, it's 1. F of x0 is 1. After that, we know that x0 is 1, h is 0.5. x0 plus h. What is f of x0 plus h? Of course, it's you cannot compute, and in mind, you can compute it using calculator. What is the value of 1.1? 1, 1 is the value of x0 plus h, but I ask you about f of x0 plus h. F of x is x power 3, 1.1 power 3. Please find this value. (1.1) is the value of x0 plus h, but we discussed about f of x0 plus h. What is the value of f of x0 plus h? 1.1 power 3. What is the value? Maybe the students who connect in Teams helps us. What is the value of x power 3 when x equals to 1.1?
10, 8, 9.
Why 10?
Cannot be 10.
It's
It's
1,331. Yes.
Because it's
It cannot be 10. 1.1 power 3.
She's divided.
No,
How to compute 1.1 power 3? It's 1.1 times 1.1 times 1.1. It's not 3. No. You should 1.1 times 1.1. The answer is 1.331. And after that, we should substitute these values into the formula. This or this, it doesn't matter. F of formula 1, f of x plus h minus f of x over h. F of x plus h minus f of x over h. You have f of x plus h, f of x, h, and f prime of x0. What will be the approximation to the real value of the derivative? Use your calculator to find the actual, the approximation to the real value of the derivative. What is the answer? Again? this. It can be computed even without calculator.
What's that say?
This minus this over this. It's very simple. 3.31. 3.31. Right? This is an approximation. This is approximation to the real derivative. We remember that the real value is 3. The real value is 3, but our formula gives us 3.31. What is the error? Error is a difference between real value and approximation. What is the error of our approximation? The difference between these two values. 0.31. It's a difference between real value and approximation. We know that the real value is 3, but our formula gives us 3.31. Very good. Now, let's compute the same, but let's take the h smaller. H equals to 0.01. Let's take h 10 times smaller. This is 1.1, but now we should compute 1.01. Please find the value of the 1.0 f of 1.01. You should just multiply it. First, you should compute the value of the function f of 1.01. F of 1, we already know it's 1. And substitute it into the formula to find the value of the derivative. Not the value, but the approximation to the value of the derivative. What is the value of the function at this point? 1.0 and something. Well, did you find the value of the derivative approximation?
One from 0, 1, 0, 3, 0, 1.
It's the value of a function or derivative? Well, the function. Yes, please tell it. 1.03
0, 3, 0,
03
1.
01. Okay, it's enough to have 3 digits after the point, but well, and after that you should apply the formula number 1, this minus this over h. F of 1.01 minus f of 1 over 0.01. It also can be computed rather simple because these values are not very hard to compute. Yeah. F prime of x equals to 3.0301. This value, this approximation, becomes closer to the real value. If you compute the error, the difference between real value and approximation, the error will be 0.03. So in the first case, error was 0.31. In the second case, error was 0.0301. The error becomes 10 times smaller. We take the h, the step, 10 times smaller, and the error becomes 10 times smaller too. Well, I can show you this effect here in the table. I use Microsoft Excel to compute the same. This is x. This is x0, 1. This is x1. This is h. The function values are 1 and 1.331. And this is the first derivative, 3.31. This table corresponds to our first case when h equals to 0.1. But let's change the step. And the function, the derivative becomes closer to the real value. The error equals to 3 minus this. 0.031. Let's take the step smaller again, 10 times smaller. And the error becomes smaller. When I take smaller h, I get the smaller error. The result becomes more correct. And for this case, you see that I have a rather good approximation to the real value. The real value is 3. Our formula gives us the answer 3.003. Very close to the real answer. Let's consider to this process from the theoretical point of view. From the theoretical point of view, the value of the function at the point x plus h can be written using Taylor's theorem. F of x plus h equals to f of x plus h f prime x plus h squared over 2 second derivative at some inner point xi. So xi is a point between x and x plus h. We don't know the exact value of the point xi, but we know that xi is between x and x plus h. If we rearrange the terms here, we can get that f prime of x equals to f of x plus h minus f of x over h minus h over 2 second derivative at a point xi. This is an equality. The left right equals to the right side. But let's compare 2 and 1. What we have in the formula 1? Here we have the exact value of the derivative. But this exact value approximately equals to f of x plus h minus f of x over h. The formula 2 gives us the error. The second term here is the error term. So now we can see this error term along with the basic numerical formula. And pay attention that the error term in the formula 2 has 2 parts. A power of h and the step h at some power. Here this power equals to 1. And a factor involving some high order derivative of f. And the h term makes the entire expression of the error converge to 0 when h converts to 0 too. It means that if we take h smaller, smaller and smaller, closer to 0, the error term becomes closer to 0 too, and the formula will be more correct. And also you see that here h is in the power 1. It means that if I decrease the h 10 times, the error decreases 10 times too. We see this effect here on this example. We take h 0.1 and we obtain the error 0.31. If we decrease the h 10 times and take the h 0.01, the error decreases also 10 times. Is it clear more or less? I think yes. Now, let's consider another formula for numerical differentiation that is called 3-point formula. You see that the precision of such numerical differentiation formula is often judged simply by the power of h present in error term. And if h is in the power 1, the convergence is not very fast. We decrease h 10 times, and the error decreases 10 times. And we can say that the formula number 1 fares poorly, as the error is of order h. This notation means that the error term has the order of h power 1. And here you may see more precise, superior formula, how to compute the value of the derivative. To find the value of the derivative at the point x, we can take f of x plus h minus f of x minus h over 2h. Let's compare it with the first one. Here we take 2 points, x plus h minus f of x over h. Here 3 points, x plus h and x minus h and f of x over 2h. So I skip these formulas. We discuss about it later. I show you their graphical interpretation. This is a point x0 and the tangent line. The real value of the derivative is the slope of the tangent line. Now, let's consider the second line that passes through these 2 points, x plus h and x minus h. You see that this second line, the slope of this second line will be more or less the same as the slope of the real tangent line. And it's almost parallel here. Let's compare with these lines. You see that this line is similar but not so close, the slope. And here the slope of these 2 lines are exactly the same. And to compute it, we use 3 points, 0, 0 plus h, and x0 minus h. Well, let's apply this new formula to our previous case. Let's consider again this function, x power 3. Let's consider x0 equals to 1 and step h equals to 0.1. How to apply this formula? You should x plus h, x minus h over 2h. The step h equals to 0.1. F of 1.1 we already compute. What you should compute to apply this formula? What value? F of x minus h. In our case, what is x minus h? 0.9.
Yeah.
Please compute f of 0.9 and substitute these two values into this formula. Well, did you compute it?
One.
What?
One.
1 comma? No, did you come 1 comma what? The final answer f prime? No, it cannot be. So what you should compute first? F of x 0.9, right? What is it? Did you compute it or not?
We did.
Yes, please tell me the answer. Zero.
1.
No, no, it's wrong. 0.01, it's wrong. Your answer?
0.27.
0.27. I think it's correct. .27. How you compute it? 0.9. I don't know why you made such mistake, because extremely simple. What you should do? 0.9 times 0.9 times 0.9 times 0.9 times 0.9. Where you lose 7? Zero point nine power 3. How you get 0.1 and how you get 0.27? I remember that it should be 27, but you lose the not 27, but 7 to 9. Or you compute it just using pen and paper. Use the calculator on phone or on computer. 0.729. And after that, if you, when we compute this value, you can substitute it here. This minus this over 2h. H is 0.1. F of x plus h is 1.331 minus 0.729 over 2h, 2 times 0.1. What is 3?
0.01.
3.01. Right. This answer is 0, 1, and I think something after. Where? This is their approximation to the value of f prime 1 that we find using this formula, 3-point formula. Let's remember that the actual value, precise value, is 3. What is the error? 3 minus 3.01. Yes, the error is 0.01. And what we see, we take the same step, the large step, 0.01, and we get the error very small, 0.01. It is smaller, it is even smaller than we get the error in previous case when we take the step 0.01. We take large step and we get very large error. And this formula gives us small error. It's very good formula. It gives us more correct value in comparison with the previous one. Well, as a task, home task, please apply this formula, 3-point formula, for step equals to 0.01. Please apply it for this step. Well, and now to finish our lesson, I skip these formulas. I only want to show you the final result. The final result, the last formula on this slide, gives us the error term. This is the actual value of the derivative. And the actual value equals to approximation value. And this is the error term. You see that here h power 2. It means that this term has order h power 2. And it's very good. Why? Because h actually is a small value. H is smaller than 1. And if we take h equals to 0.1, the error term will have the magnitude of 0.01. h power 2, h squared. If you take h equals to 0.01, h squared will be 10 power minus 4. It means when you decrease h 10 times, the error decreases 100 times. So you decrease the h 10 times, but the error decreases 100 times. This formula is very good in comparison with previous one. The previous formula, if you decrease the step 10 times, the error decreases also 10 times. It's good, but it's not very good. But here, if you decrease the step 10 times, the error decreases 100 times. This is the error term of this differentiation formula. Well, next week we discuss about the second derivatives, and we consider how to find the formulas for numerical differentiation of the second derivative. We consider how to derive this formula from the numerical interpolating. comes from the interpolating polynomials. And well, according to your timetable, the next week will be, the next lesson will be 9.10. Right, we have 2 lessons actually, and next week we have, as usual, we start at 9.10. Let's finish. I close my presentation.
So next week is at the same time as today.
So I close the window.
Next week is at the same time as today, sir.
Not only, yes, I stop recording. And